Hello. In this lecture, we will be mainly focusing on the analysis of algorithms. We will begin with the definition of an algorithm, understand its features, and learn what is meant by order of growth by analyzing two sorting algorithms, namely insertion sort and merge sort. This lecture covers chapters 1 and 2 of your main reference book. So, where did the term algorithm originate from? It is actually the Latinization of the name of the famous mathematician Al-Khwarizmi, a name which I believe you must have all heard about. He had written a numerical system book, which was translated into Latin as Algorithmi on the Numbers of the Indians, where algorithmi was the translator's Latinization of his name. Before delving deeper, we need to make sure that we all understand clearly what an algorithm means. The three most appropriate definitions for the term algorithm are given over here. It is a sequence of computational steps that transform the input to the output. It is a procedural approach to solve computational problems. The definition given by the authors of the book, however, states that it is a theoretical study of computer program performance and resource usage. Please pay attention to the terms performance and resource usage. Now, a very important question that arises is that what is more important than the performance of a computer program? Interestingly, this is a question often asked in interviews in software development industry. As an engineer and programmer, you should be able to come up with these features. The first one is correctness. You should make sure that the program you develop works correctly on all valid inputs and not only for a selected subset. Then we have simplicity. It should be simple to understand and probably change the code in future if needed. Maintainability. You should be able to update the code with minimal effort. Robustness or stability, which refers to the fact that your code should not freeze or stop working abruptly. One of the most important features is modularity, where the code should be broken down into smaller parts. Doing so allows us to concentrate on the part that we need to change without having to worry about the remaining of the code. It also allows for code reusability, which means write once and reuse many times. Security is another feature which should protect the code from being attacked intentionally. A very simple example of security can be seen in object-oriented programming, where we have the abstract entities called classes. Scalability means expanding the program to serve more users without sacrificing any of the other features. Finally, user-friendliness is very important as it provides an interface that should be able to allow the user to use the best of the program. If you look at these features carefully, you see that these all features actually revolve around performance. Believe it or not, we use algorithms in our daily routines more often than we think. Let's look at some simple examples. Suppose you want to attend a lecture on algorithms at MIT and you want to take the shortest path. What you do is you open Google Map and you see that it gives you the shortest travel time within seconds. Magic? No, it just simply runs the shortest path algorithm, which actually we will be studying later on in this course. Related to this, I would like to ask you a very interesting question. Is it true that the shortest path is always the fastest path? Let's take the example of a lifeguard running towards a drowning person. So, this is the scenario. Would the path 1 be the shortest one, or would path 2 be the shortest one? Well, obviously path 1 is shorter than path 2. But what we should keep in mind that even though path 1 is short, lifeguard will have to swim towards the drowning person, which obviously will take more time than running along the coast and then swimming for a shorter distance. Therefore, even though path 1 is shorter than path 2 would actually be faster than path 1. The next example refers to data compression, which is a process of reducing the size of the original data by representing it with fewer bits. The data compression techniques that are mainly used can be classified into two types: lossless and lossy methods. The difference between these two methods is shown in the picture over here. In the lossless method, the original data is compressed into a smaller amount, but upon restoring, you get back the original data without losing any information. On the other hand, in the lossy approach, the original data is reduced to a much more smaller size as compared to the lossless counterpart, but upon restoring the data, you actually lose some lesser important information and you do not get back all the original information. A very simple example would be the resolution of pictures. For example, if you compress a picture, it has some resolution. Upon restoring it using the lossy method, you would not get back the same resolution as you originally had. We are all familiar with PageRank, right? It is the main algorithm that is used by Google search engine to rank the web pages based on the user's search keywords. It is the algorithm that made Google what it is today. Now, the question is, how does it work? The main aim of Larry Page, the inventor of PageRank and the co-founder of Google, was to list the pages based on their importance or relevance to the query. So basically, the PageRank algorithm is a voting algorithm where all the pages on the web are allowed to vote about the importance of every other page on the web. So if you look at the figure given over here, we see that we have a page called D, which has one link pointing to it from page E and has two links pointing out to page A and page B. So in this scenario, a link to a page is considered as a vote of support. If there is no link, that means that page is not supported or not important. Now let's assume that we have a page A and that page has n number of links pointing to it. Let's denote them by T1 to Tn. Now, we assume that the surfer who is searching on the web and is clicking the links would probably stop at some point. So the probability that at any time the surfer clicking on the links will continue is called the damping factor, which is denoted by D. Studies show that this factor is some value around 0.85. Then we have CA, which is the number of links going out of a page. For example, for page D, C of D would be 2. There are 2 links leaving page D. Then the equation is a very simple equation, which is a weighted equation in terms of D and the page rank of each of the pages pointing to A. So the page rank of the page rank of page A would be function of D and the page ranks of all the other pages that are pointing to A. So one may question, okay, to find the page rank of a given page A, we need to know the page ranks of all the other pages pointing to A in prior. That means we need to know what PRT1 is, PRT2 is, and PRTN is. But we do not know that. And to calculate that, again, in that equation, we have to know the PR or page rank values of all the pages pointing to each of these pages. And this keeps on continuing forever. So how can we calculate the page rank of a given page? Well, we can go ahead without considering that, and we'll show you how to do that in a couple of examples. Let's look at this very simple example where we have two pages, page A and page B, both pointing to each other. So if you would ask me, I would say, to me, both the pages look equally important. But how do we show that mathematically? Well, we see that there is one link leaving page A, so C of A would be equal to 1. Similarly, there's one link leaving page B, so C of B would also be equal to 1. Now, we need to write down the equations for both of these pages. So what we have is an equation for PR of A and an equation for PR of B. But as you see on the right-hand side, we need to know their page rank values in order to calculate the page rank value of the other page. So one way to approach this is to make a guess. And in this guess, we take it to be equal to 1. So if we plug in 1 over here, what we get is PR of A would be equal to 1. And then we take this one, which is PR of A, and we put it in this equation to calculate PR of B. And that would also give us equal to 1. So we made a very lucky guess, and this led us to conclude that both these pages have the equal values of 1 and are thus equally important. Now in our second guess for the PR values, let's assume that PR of B and PR of A are both equal to 40. So in that case, what we would do is we would plug in 40 over here in the equation for PR of A, and we get some value. Then we plug in this value, which is 34.25, in the equation for PR of B, and we get 29.1775. And now what we do is we recursively keep doing this. That means again, we take this value, which is 29.1775, and put it here in equation PR of A to recalculate it, and we get a lower value as compared to what we obtained in the first calculation. So as you see, in every iteration, the PR values for both the pages keep decreasing. So basically, if you keep reiterating the calculations, you would see that the values that we compute for page rank of A and page rank of B would converge to a fixed value, which was equal to 1 in our very initial guess. So irrespective of your initial guess, the page rank algorithm would always converge to a fixed value. If you look carefully, this is exactly the same as solving a system of equations with two unknown variables and two equations, which we all know how to do. Now that we have the definition of algorithm out of the way, it is important to know that in order to design an algorithm, we should be able to first analyze it. What do we mean by analyze? We mean we should be able to know how efficient it is in terms of time and space. If you recall, I had previously asked you to keep in mind the two keywords performance and resource usage. Well, performance can be mapped to time, while resource usage can be mapped to space. So the definition for time complexity is developing a formula to predict how fast an algorithm would perform given the input size. Similarly, space complexity is getting an algorithm or getting a formula that would tell us how much memory an algorithm would use in order to solve the problem efficiently based on the size of the input. Now, in this course, time complexity is what we will be more focusing on rather than space complexity. And the reason is because the memory or space is extensible, but time is not. There may be many algorithms available that actually solve the same problem. But the algorithms that actually matter are the algorithms that would be more efficient and in terms of complexity would have lower time complexity. So we need to work and understand how an efficient algorithm performs within some given time bounds. In this example, we see the students are asked to find the product of 18 times 5, and each student has come up with a different way to solve the problem. As we all know, in terms of hardware, it is much more easier to perform multiplication and division as compared to addition and subtraction. All you have to do is just move the bit stream to the left or right. With this in mind, we realize that Ricardo has actually come up with a more efficient way to solve the problem as compared to his classmates, because his solution only involves multiplication, while the other solutions involve either addition or subtraction. So it is very important to make sure that you choose the right data structure to implement an algorithm. Data structures help creating programs that are simple, reusable, maintainable, and has all the other features that we studied about earlier. Now let's use a comparative analysis to understand what efficiency actually means. Here we have two sorting algorithms, namely insertion sort and merge sort. As for now, let's assume that the running time of insertion sort is proportional to C1 times n square, whereas that of ms is proportional to C2 times n times log of n. Over here, n is the input size. Say an array of size n is equal to 15, for example. C1 and C2 are constants that are independent of n. Therefore, the impact of these constants is negligible. Note that the running time of insertion sort depends on n, while that of merge sort has a factor of log n. To understand the relation between n and log n, let's look at this example. So when n is equal to 1000, the log base 2 of n would be approximately 10. Whereas when we increase n by an order of magnitude of 1000, then log base 2 of 1 million would be approximately 20. So for small values of n, insertion sort may run faster. But as we increase the size of the input, merge sort will actually compensate for the difference C1 minus C2. Now let's look at a more practical example. Say that you are given 10 million integers and you're asked to sort the numbers. And each integer is represented using 8 bytes. So you can obviously calculate how many megabytes of data that would be. Now assume you are given two computers, computer A, which is a more modern and fast computer, and computer B, which is an old and much slower machine. On computer A, we intend to run the insertion sort. The speed of this computer is 10 giga instructions per second. And we put the best machine language programmer to implement insertion sort on this fast computer. We already know that the running time is proportional to C1 times n squared, where in our example, C1 equals to 2. On the other hand, we have computer B, and we run the merge sort on this slower computer. The speed of this computer is 10 mega instructions per second, which is far much lesser than that of computer A. And we put an average high-level programmer to implement merge sort on computer B. In this case, C2 is equal to 50. So under this setting, can you guess which computer would sort the 10 million numbers faster? We can calculate the time taken on each computer by taking the running time and dividing it by the execution time of each processor of each computer. So for example, for computer A, we had 2 times n squared, where n was equal to 10 million numbers. And if we plug it in here, we see that this would give us something around 5.5 hours. On the other hand, if you look at computer B and you consider 50 times n times log n, and you divide it by the execution speed of that computer, you would see that it would take less than 20 minutes to sort the 10 million numbers. So what we can conclude from this example is that even though merge has a slower growing running time, as the input n increases, at some point, which we call n naught over here, we would see that it would perform much more better than the insertion sort. So the lower the running time, the more efficient the algorithm would perform for sufficiently large values of n. Now it's time to actually understand how each of these two algorithms work. First, let's begin with the insertion sort. So in any sorting algorithm, what you are given is a sequence of n numbers, which over here we denote as A1, A2 until AN. And the output of the sorting algorithm should be a permutation of this n input values such that they are in either the ascending or descending order, which over here we denote as A prime 1, A prime 2 until A prime n. So for example, if you are given the numbers 1, 9, 2, 5, 7, and 9 as input, after sorting that in an ascending order, the output should actually be 1, 2, 5, 7, 9, 9. In case of insertion sort, if you are given, for example, such an input value, and you are asked to sort it. So what you do is basically the same as you would do with a hand of cards. If you are playing cards, you already have one card in your hand and you take another card from the deck. And then you compare it with the card in your hand. If the value of the new card is lower than the card that you already hold, then you put that card on the left side of the card that you already hold. If the value of the new card is greater than the card that you have in your hand, then it doesn't swap and you place it on the right of the card that you already have. Therefore, in this case, what we see is that you always start comparing with the second element in the array. So if 4 is the card that you already have in your hand, you take the next card, which is 3, and you compare it with 4. Is 3 lesser than 4? Yes, so you swap them. And that's what is shown with the green numbers. After swapping, you see that the green numbers are already sorted. Then you take the next new card, which is 1, and you compare it with its neighbor, which is 4. Is it lesser than 4? Yes. Then you swap it with 4. Then you compare the 1 with the next neighbor, which is 3. Is it lower than 3? Yes. So you swap it with 3. And after that, there's no other value to swap with, so this side would be sorted. Then you take the next card, which is 6, and you do the same over and over until you see that all the numbers are sorted. So what you should keep in mind is that until you pick up the new card, every other card to the left or the cards that are in your hand are already sorted, while every other card that are on the deck or the pack have not been sorted yet. So this is what we call an invariant, and we will study about it. Over here, we see the pseudocode for the insertion sort. So in the pseudocode, you see that a function takes an input A, where A is the array of size n. And we have two loops, a for loop and a while loop. Inside the for loop, we start from the second element or the second card. So we say that you take the second card, put it in a variable called key, and we have to find a position for this key to insert on the sub array to the left of this new key. So inside the for loop, we have another loop called the while loop. And this while loop actually looks for that position and it compares it with values to the left of the key. Once it finds the position, it replaces it and shifts every other element to the right to open up space for this new value key. And it keeps doing this until the value key is not smaller than anything else to the left. So we can say that the insertion sort is what we call an in-place sorting algorithm. Now, what do you mean by in-place? In-place means that it rearranges the numbers inside the array itself without using any auxiliary or extra memory space. This is a graphical explanation of another example where insertion sort is used. So if we have this array where the numbers above these boxes indicate the index of these houses, and the numbers inside the boxes are the values held in each house. So what I would say is A1 has number 5, A2 has number 2, A3 has number 4, and so forth. Now, according to insertion sort, as I said, we begin with the second value, which is 2. So this will be our new key, and we compare this with every value before it or to the left of it until we find the right place. So we compare 2 with 5. Is 2 lesser than 5? Yes. So we swap them. And since 2 is the first element in the array, we do not go any further. And all we do is we increase the index from 2 to 3. Now we do the same thing for 4. 4 is compared with 5. They swap. 4 does not swap with 2 because 4 is greater than 2. And over here, we move to the next number and so forth. So the red line over here actually is very important. This line tells us that every number to the left is actually already sorted, while every number to the right has not been sorted yet. And as I told you, this is a very unique feature of this sorting algorithm, which we call invariant. So if J denotes the index of the house, and A of J is the value inside that house, I can say that every number or every sub-array to the left of this red line is already sorted, while all the numbers to the right of this red line have not been sorted yet. So the left part is actually this sub-array, and the right part is actually this sub-array. So the loop invariant property of this sorting algorithm says that at the beginning of the for loop that we saw in the pseudocode, the sub-array 1 to j minus 1, the gray ones, consists of the elements that were originally in the same places, but now in a sorted order. You see that 2, 4, 5, 6 were actually in the same place, but they were not sorted in A. But when you reach D, you see that they are sorted and they are again still in the same places. That means they are in the same subarray. So this is what we call the loop invariant property. Now you may wonder why this loop invariant property is so important. Well, to prove the correctness of any algorithm, we normally try to find what the invariant property of that algorithm is. And to do that, we have to go and conduct 3 different steps. The first step is the initialization step, the maintenance step, and finally the termination step. So if the loop invariant property holds for all these 3 steps, then we can confirm that this algorithm is correct and it would work correctly for any input. Now to understand why the insertion sort is correct, let's use the loop invariant property for each of these 3 steps. In the first step, which is initialization, we see that the loop invariant property should hold true before the beginning of the for loop. So it should be true before the first iteration of the for loop. In that case, j is equal to 1, and it is the only element to the left of the red line. And since it's the only element, it is already sorted. The next step, which is maintenance, we prove that this invariant is true for any value of j from 2 to n. And you see that in the previous example, as we showed, as the red line progresses, this loop invariant actually is true. In the final step, the termination step, we say that the loop invariant should actually be true even after the for loop finishes execution. That means when j becomes n plus 1, which is 1 more than the actual length of the input size, we can substitute j is equal to n plus 1 in the loop invariant statement and get what we see over here. With this substitution, the statement reads subarray A1 to n, which is actually the entire array, consists of all the elements originally in 1 to n, but in a sorted order. And this is exactly what the loop invariant is for insertion sort. So since it holds for all three states, it is a loop invariant that proves the correctness of this insertion sort algorithm. Now we want to analyze the running time of insertion sort. So to do so, as we mentioned earlier, computational time is what is more important to us. So we consider the random access machine model or RAM model to analyze the algorithms. What is RAM? You can look at this link for more details. So to analyze any algorithm, we have a bunch of assumptions. If we are dealing with for loops or while loops, we say and we know that every loop ends with one extra iteration. So if a for loop is to iterate for n times, we know that it always makes one additional iteration in the end and checks the condition whether it holds or not. And at that stage, it is false and it doesn't enter the for loop. So every instruction I within a for loop actually takes some constant time to execute. And we assume that that constant time is denoted by Ci. So the running time of an algorithm would depend on the input and it grows with the size of the input. So basically what we're trying to say is that the running time will always be a function of the input size, which is n. In this slide, we want to analyze the running time of the insertion sort. You see the pseudocode for the insertion sort on the left and two new columns, cost and times, to the right. Inside the insertion sort, we have 8 instructions. The first instruction is a for loop, which goes from j is equal to 2 to a dot length, which is basically n. So the for loop iterates n minus 1 times. But according to our assumption, a for loop or a while loop will always make one extra iteration before it stops. So we have n minus 1 plus 1, this is plus 1, which would give you n. Now instructions 2 to 8 are inside the for loop. So each one of these instructions would run one time lesser than the number of times the for loop is executed. The cost column is the fixed value which is associated to each instruction as per our assumption. So instruction 1 has a fixed cost of C1. Instruction 2, which is an assignment instruction, is inside the for loop and therefore it runs n minus 1 times and it has a fixed cost value of C2. The third instruction is a comment, which has no cost because it is not executed by the compiler, but it is seen n minus 1 times. The fourth instruction is again an assignment instruction, which has a different cost value, which is C4, but it has the same number of iterations as instruction number 2. Now we get to instruction number 5, which is a while loop. And this is a very important point. So for every iteration of the for loop, we do not know how many times a while loop would execute. So depending on the key value, the while loop may not execute at all and you may not get into 6 and 7. A while loop may execute once, twice, or n minus 1 number of times based on the key value. So for example, if the key value or the card that you pick from the table is the largest number as compared to the cards in your hand, so there would be no swapping. And therefore, the while loop would not be executed at all. But if this key value is some value which is between the numbers that you hold in your hand, you would have some number of swappings. But how many? We do not know because we do not know the order of the input. In the worst case, if the key or the card that you pick up from the table as the smallest value, then you would swap it with each and every number that is to the left of the red line. And therefore, the while loop would be executed the maximum number of times. Due to this, we cannot exactly determine the number of times that the while loop would be executed for each iteration of the for loop. And that's why we use the term Tj. It says that for the iteration j is equal to 2, we have T2 number of iterations or executions of the while loop. Okay, so if j is equal to 3, we would have T3 times execution of the while loop. And keep in mind, based on our assumption, the while loop always has one extra execution. So everything inside the while loop will always have a -1. Therefore, we have Tj -1 for every instruction inside the while loop. The last instruction, which is instruction number 8, is outside the while loop, and it is an assignment instruction. And that's why it would have n-1 number of executions, similar to instruction number 2 and 4. So if we denote the running time of any algorithm based on the value of n, which is the input to that algorithm, as t of n, as shown over here, we can compute t of n very easily. It is actually the sum of the product of these two values. So basically what you do is you multiply these two, multiply these two, multiply these two, these two, these two, and till the end, and you sum them up. That would give you the value of Tn, which is the running time of any algorithm. So if we sum the product of the cost and time values given in the previous slide, we would eventually end up with this equation, where each term corresponds to each instruction in the pseudocode. This term corresponds to the first instruction, this second instruction. The third instruction was a comment, so it has no impact over here. Then we have the fourth instruction up till the eighth instruction. Now let us look at what would be the best case running time for the algorithm and the worst case running time for the algorithm. When would the best case occur? The best case will occur when the input given to you is already sorted. This means that you would not have to have any swapping done within the algorithm. In other words, the while loop would never be executed. So if we look at this equation, T of n, and we look at the terms related to the while loop and instructions within the while loop, which are these three terms, we see that this term would actually reduce to summation of 1. Because based on our assumption, the for and while loops, they have one extra iteration. So the summation of j from 2 to n of 1 would be n-1. And since we have replaced tj with 1, 1 minus 1 would be 0. And therefore, we do not see the terms related to the instructions within the for loop, within the while loop in this equation. So if we rearrange these terms and write them as such, we see that this coefficient is actually some constant a, and the sum of these coefficients is some constant b, and this is a linear equation. So we can say that the best case running time of an algorithm, in this case insertion sort, is a linear function of n. Now, when would the worst case occur? The worst case would take place if the input given to you is in the descending order or reversed order. It means that every new card that you pick will have to be swapped with each and every card in your hand. So if this has to be the case, these three terms would have a different summation. So in the worst case running time, you replace tj with j. Why? Because for every iteration of the for loop, you will have the maximum number of swapping within the while loop. And therefore, the summation of this would eventually be this. And since these two instructions correspond to instructions within the while loop, they have a -1. So summation of j minus 1 would be this. Now, if you rearrange these terms again in terms of n, you would get a quadratic equation. So we can say that in the worst case, the insertion sort would be a quadratic function of n. Now that we have seen how to calculate the best case and worst case running time for the insertion sort, we would like to concentrate mainly on the worst case running time. That is the longest time for any input of size n to be sorted. And why is that? It's because the worst case running time of an algorithm gives us an upper bound on the running time for any input. That means if I know that the worst possible input to an algorithm would give me some time, then the algorithm would never execute or take more time than that time. Now that we have seen how to calculate the best case and worst case running time for the insertion sort, we would now like to concentrate mainly on the worst case running time. That is the longest time for any input of size n to be sorted. And why is that? It's because the worst case running time of an algorithm gives us an upper bound on the running time for any input. It means that it gives us a guarantee that the algorithm will never take any longer time. So in reality, for most algorithms, the worst case occurs quite often than we expect. And the worst case running time is normally the same as the average case running time for most algorithms. Now you may ask, what is average case? The average case analysis of an algorithm actually depends on the statistical distribution of the input. So if I have an input array of size n, and I know the probability of occurrence of each permutation of that array, then I have a distribution. And based on that distribution, I can calculate the expectation. That is known as the average case. More on this would be studied when we get into randomized algorithms. But for now, all that you need to know is that our focus would be on analyzing the algorithm in their worst case scenario. That means the worst case running time is what is important to us because it gives us the maximum time needed for an algorithm to give us an output. Now I'm going to show you a trick to quickly calculate the order of growth of an algorithm. We saw that the worst case running time for insertion sort is a quadratic function of n, which is given over here, where a, b, and c are coefficients in terms of the cost ci. So there are two steps to this. First, find the leading term, which in this case is a(n square). Remove the lower terms. This is because as n grows sufficiently large, the lower terms have no impact on the growth of the leading or dominant term. After doing so, in step 2, remove the coefficient of the dominating term. That's because the coefficient is just a scaling factor and does not impact the computational efficiency of the algorithm for large values of n. So you are left with n squared, and that's it. What you have to do is just write the worst case running time for insertion sort is theta of n squared, which is given over here. So when we want to compare algorithms based on their efficiency, we would look at their worst case running times. So the algorithm having a lower order of growth would be the algorithm that we would consider being more efficient. For example, if you have two algorithms, one theta n square and the other theta n cube, so which one would you consider to be more efficient? Obviously, if you look at this graph, you will see that n cube would be growing much more faster than n square. So we would say between these two, I would prefer n square. Now here is an example. If this is the running time for some algorithm, say algorithm X, and I ask you to find the order of growth, what would be the order of growth for this algorithm? So what we have to do is look at the leading term, which in this case is this, because we have n cube. Remove the lower terms, In the leading term, remove the coefficient, which is 1 divided by 1000, and you're left with n cubed. So my answer would be theta n cubed. As we have seen so far, algorithm design and algorithm analysis go hand in hand. The design of an algorithm can take two different approaches. One approach is the incremental approach, and this is the approach that we use in insertion sort. What does it say? It says that if you have a hand of cards and you take a card from the table, you sort this card inside the hand of cards one by one. It means that you add elements to the sorted subarray one by one until you have picked up all the cards from the table. So the subarray A of 1 to j minus 1 are basically the cards that you already have sorted in your hand. And the next card, that means A of j, would be the key that you pick from the table. And when you sort it in your hand of cards, the size of that subarray would increase by 1. And so you would have one added card to your hand of cards, and that added card would also be sorted. So we are increasing the size of the sorted subarray one by one. The other approach is divide and conquer. And this is the approach that we will be using to design the merge sort. And interestingly, this gives us a lesser worst case running time as compared to insertion sort. All recursive algorithms fall under this category. So there are 3 steps to the divide and conquer approach. The first thing is you have a problem, you have to divide it into subproblems. The subproblems have the same structure and features of the main problem. Once you have the subproblems, you conquer them by solving them recursively. That means you again break the subproblem into sub-subproblem, then that sub-subproblem into smaller problems until you reach the case where the problem is solved for a very small size. Once you have the solution for the smallest size problem, you merge them and you recursively go up and you get your final answer. So we have divide, conquer, and combine. Now let's take a look at the divide and conquer approach in action. As we said, we implement the merge sort using this approach. The pseudocode for the merge sort is given over here, where the inputs are the array A, P, and R. P and R refer to the indices of the first and last element of array A respectively. So basically what this algorithm does, it divides the array into half and it solves each half recursively. So if P is less than R, that means if the size of the smaller problem is not 1, what we do is we divide it into half and we call the function recursively to solve each half. So basically, the first recursive call we give from P to Q, which is over here. And the second recursive call, we give the indices Q plus 1 to R. And the algorithm keeps solving this recursively until the condition P greater than equal to R is satisfied. This means that the subproblem has reached the size 1, which is a single element and is already sorted. When that happens, it combines the solution and it recursively returns it back and merges it in the function merge, which is given in the 5th line. If n is the size of your array A and n is an even number, then Q would be equal to n divided by 2. And we would have 2 equal halves. But if n is odd, then we would have to use ceiling and floor operators to divide the array into 2. Over here, we have the pseudocode for merge, which was given on line 5 in the previous slide. So basically what we have over here is the 2 subarrays or the 2 halves of the original array. On line 1, we see we have n1, which is a variable, and it gives us the length of the first half of the array. n2 is the length of the second half of the array. We define two new subarrays, L and R, which denote left and right. And what we do is we copy the first half from A into L using this for loop, and we copy the second half of A into R using the second for loop. And the last element of the L and R arrays, which are the new arrays, are placed with an infinity sign, which is actually a sentinel used as a marker to show that this is the end of the array. You can do the implementation actually without having this extra space, but this is what is given in your textbook, and for sake of consistency, I have just put it as such. Now what we have to pay attention to is what is happening between lines 10 to line 17. We see that there is a for loop, and in this for loop, there is some assignment. So let's look at an example to understand this better. So in this example, we see that at some point we have an array A, and the size of the array is 8 elements. So we have even number of elements, so we divide them into 4, 4 in the arrays L and R that we discussed earlier. So the first 4 elements go into L, and the last 4 elements go into R. We have the indices K, I, and J as in the pseudocode. So the first step would be to check the first element in A with the first element in R. The one which is lower or lesser would replace the element over here in A. So we see that 1 is lesser than 2. So we replace the 2 which was here with this 1. And then what we do next is we move the index j to the next element. So now we have to compare 2 with the next element, which is also 2. So since both of them are equal, it doesn't matter which one you choose. In this example, we choose this 2. So we replace 4 with 2. So 2 goes over here. Now we move the index I and we compare the second element in L with the second element in R. 4 and 2. So 2 is lesser than 4, so we replace 5 with 2, which we see over here, and we move the index by 1. And we keep doing this till we reach the sentinel, which is the infinite sign. So once we reach this infinite sign, we know that we have reached the end of L and R, and we have already sorted the array. So the flowchart representation of the merge sort would look something like this. For this particular input, we divide it into half, so we get these two almost half subarrays, and we keep dividing them until they reach a size of 1. Since we know every element is already sorted as it cannot be compared with any other element, so what we do next is then we merge them. So we merge these two, and we know that when you merge them using the merge function that we saw, they will be sorted. And this will be sorted, and so we have subarrays which are being merged in sorted order. And we keep doing this until we reach or find the solution for the actual problem, and this would be the sorted solution for this given input. Similarly, this can be used to actually sort strings. So if you have strings or string as such and you want to sort it alphabetically, you can use the merge sort. It should be noted that in the merge function, the arrays L and R, which are the solutions to the subproblems, are already sorted. So for example, if you look over here, we have L and R, which are already sorted. Okay, so once we know this, we can define the loop invariant property for the merge sort. So this property tells us that at the start of each iteration of the for loop, which is on line 12 to 17, the subarray A from P to K minus 1 contains K minus P smallest elements of L from 1 to N1 plus 1 and R 1 to N2 plus 1 in a sorted order. Also, Li and Rj are always the smallest elements of their arrays that have not been copied back into A. So what does this mean? Let's go back to this example. It says that As k progresses, the elements that are brought back or put back into A will always be the smallest element in L or R. So as you see, we put 1 here. So 1 was the smallest element in R. It's not that you can choose any other element over here. Why? Because L and R are already sorted. So as K increases, anything that is put back into K, okay, so any sub-array of A will always be sorted, and the elements in here are actually the smallest elements that were chosen from L and R. Now we will use this loop invariant property to show the correctness of merge sort. The initialization step tells us that, okay, before the start of the first iteration of the for loop, okay, we have k is equal to p. That means the array A from p to k minus 1 is empty, and it contains none of the smallest elements of L and R, which is true. And L1 and R1 actually hold the smallest elements in their arrays, which have not been copied into A, because k is equal to p and k minus p is equal to 0. The same argument holds for the maintenance step and the termination step. It has been very clearly detailed how to explain the correctness, so I leave it up to you to understand how to do this. Now let's try to find what is the running time of the merge function inside the merge sort algorithm. This is the pseudocode that I've copied again, so look at it and let's work it out together. The first thing that you have to do is to look for the for or while loops in this procedure. So instructions 1 to 3 are basically just assignments and initializations, so they take constant time. The first for loop can be seen on line 4. This for loop iterates from 1 to n1. Okay? The second for loop is on line 6 and it iterates from 1 to n2. So the sum of these two for loops would be n1 plus n2, which is n. Therefore, we have worst case running time of theta n. Lines 8 to 11 are simple assignments and thus have constant time. So we have to now focus on line 12, which has another for loop. In this for loop, we see that k iterates from p to r. Since p is the first index of the array and r is the last index, and we know that the array has a size of n, therefore this for loop would iterate n times. Therefore, we would have theta n over here. So by comparing the three for loops, we conclude that the worst case running time for the merge procedure inside the merge sort algorithm is actually theta of n. An algorithm that is designed using divide and conquer approach will contain recursive calls to itself. To find the running time of such algorithms, we use what is called the recurrence equation. So if we have a problem of small size, say n is less than or equal to some c, where c is a constant, then we would say that it takes some constant time to actually find the solution to that problem. In the merge sort, c is equal to 1. That means when the size of the subarray reduces to one element, then it has nothing to be compared with and is thus sorted. So the time it takes is some constant time, theta 1. Also assume that in a divide and conquer approach, the actual problem is divided into n sub-problems. In merge sort, this A is equal to 2 because the array A is divided into half at every iteration. Also, the size of each sub-problem would be 1 divided by B times the size of the original problem. We know in merge sort, the size of each sub-problem is half the size of the actual problem. So A and B would be both equal to 2. Now let D of n be the time to divide the problem into sub-problems. That is, D of n is the time taken to calculate the middle point Q. Let C of n be the time to combine the solutions of the sub-problems to get the solution to the actual problem. With all these definitions in place, we would have this recurrence equation, where T of n is the worst case running time of the algorithm which is designed using divide and conquer approach. It would be equal to theta 1 if the size of the input is less than or equal to some constant c, or it would be a recurrence equation in terms of t if n is greater than c. For the sake of analysis, we assume that the input size n is a power of 2, even though the analysis would work well if n was an odd number. So if we make such an assumption, in each step, the problem is divided into exactly 2 halves, and the size of each half would be n divided by 2. If we want to apply merge sort on a single element, we told you that it would take constant time theta 1. But what if n is greater than 1? Returning back to the worst case running time analysis for the merge sort, let us break down the recurrence equation into 3 parts. In the divide phase, d of n is actually the time taken to compute the middle point q. And therefore, since it is just the sum of 2 numbers divided by 2, it takes constant time theta 1. The next phase, which is a conquer phase, actually recursively solves each subproblem of size n divided by 2. And this actually contributes to the term 2n divided by 2, which is seen over here. The last phase, which is combine, is actually the merge procedure that we have already studied, and we found that the running time over there is theta n. So by adding them up and replacing them in the divide and conquer recurrence equation that we've already seen, we see that if n is equal to 1, t of n would be some constant time theta 1, and if n is greater than 1, we would have a recurrence equation where this term is actually from the conquer phase, this term is from the combine phase, and this term is from the divide phase. So we know that this is constant, and if n grows sufficiently large, this would make no sense, so we can remove it, and eventually we would get this recurrence equation. The next step is to prove that the solution to the recurrence equation is actually t of n is equal to theta of n times log base 2n. And how do we do that? We will see over here. We can rewrite the equation which was obtained earlier as such, where we replace theta 1 by constant c. So it's the constant time required to solve a problem of size 1. Similarly, when we have a problem of size n, we can solve it with c times n. So with this new recurrence equation, what we do is we construct the recurrence tree, and then we add the costs across each level of the tree to compute the total cost of Tn. The next slide shows us how to do it. Before we draw the recurrence tree for the merge sort algorithm, we should remember that n is a power of 2. So given t of n, what we can do is we can replace it with the equation that we obtained in the previous slide. So the recurrence equation would replace t of n with c times n, and this would have 2 subproblems, each having a running time of t of n divided by 2. Now we can again replace each of these subproblems into their sub-subproblems. So t of n divided by 2 can be replaced by c times n divided by 2, each again being divided into halves, where n divided by 2 would give you n divided by 4. Keep doing this until you expand the whole tree and you reach the last level where the size of each problem is 1. That means there are n number of single-sized arrays on the last level. So level 0 contains 1 node. Level 1 contains 2 nodes. Level 2 contains 4 nodes. And if we keep doing this, we reach the last level where there would be n number of nodes. So we can generally say level I contains 2 to the power I number of nodes. So to calculate the level of the tree, that means the last row, what we have to do is we have to just replace it with n. So taking log on both sides would give us log base 2n. Therefore, we would have 0, 1, 2, up till log n number of levels. So in total, there would be log n plus 1 number of levels because we start from 0. Now we want to calculate the cost across each level. So we see the number of elements in each level. Level 0 has one element, so the total cost would be Cn. We write it as such. Level 1 has two elements, so the cost would be the sum of these two, which would again be Cn. Similarly, adding up all these nodes would give us the cost for level 2. And finally, for the last level where we have arrays of single size elements, so the cost of sorting each of them would be some constant value C, and there are n of them, so it will be n times C, which would again be the same. So we see that the cost across all the levels is the same. This slide summarizes exactly what I just talked about. Let's pay attention to the last 2 points. So using induction, we can actually prove that the total number of levels of the recurrence tree for the merge sort would be log n plus 1. I highly recommend you to try this out and do it as practice. Finally, what we have is log n plus 1 number of levels, and the cost across each level is Cn. So the total cost would be the number of levels times the total cost, which is log n plus 1 times Cn. That would give you this value, and since n grows sufficiently large, this would be the leading term because it has n times log n, while this is only n. We can remove this, and therefore we would have the worst case running time to be theta of n times log n.